Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're gonna discuss and spot the light briefly on uncommon topic related to construction field. As engineers, we are looking forward to find the best material to achieve the equation of quality, cost, safety, sustainability with environmentally friendly. One of these material is Gfrp, which is the main item in our topic today. So the question is, why Gfrp? And can Gfrp partially or fully replace steel bars? As we know, the normal steel bars have a lot of disadvantages and a bad impact on the environment on the long term, especially. So we want a structure with amazing properties, criteria, and achieve what we want as engineers. So we want to take the advantages of each material and combine this privilege together. So as we see, Gfrp have higher strength durability with lower overall cost, amazing corrosion resistance with less weight compared to normal steel bars, innovative solution for sustainable construction, and amazing non-magnetic properties. In the same time, each material have disadvantage also, and one of the bad and main disadvantage of Gfrp is the brittleness. That's why Gfrp is uncommon in normal buildings like residential or commercial building. It's just used in specific projects like marine structures underground, some have bridges, as we see in these photos, swimming pool, maybe parking, just specific structures. On the other side, we all know the amazing advantage and the super magic of pre-stressed systems. And this slide show a real project showing pre-stressed cables with steel bars, and this is the most familiar mix, as we say. So to sum up uh, what we said, what do you want to get? What is the purpose of these slides? We want the advantage discussed of Gfrp bars, and in the same time we want to overcome the disadvantage of brittleness. So how can we do this? Are we magicians? No way. Uh, to make this combination, we suggest adding Gfrp bars with pre-stressed cables instead of normal steel bars to achieve what we want. So, is it applicable or not? We will see. This is a case study from my thesis with the name of flexural behavior of fully pre-stressed bonded post-tension concrete beams reinforced with steel or GFRP bars. A long name, I know. So the motivations, why? The research on efficiency of using this combination is so limited. Almost no real project is executed like that. Even research is not enough in this topic. Also, design codes lack guidelines on how to design this combination. Also, the importance of this combination environmentally, especially as we mentioned before. So we will see my thesis, can we get what we want or no? The outline of my thesis is experimental program, results, comparison with some international code, conclusion and recommendations. So the main specimens are shown in these slides. Beam with GFRP or steel with strand, beams with steel only, beams with GFRP only, with the shown dimensions and section. So TS refer to cable with normal steel bars. TG refer to cable with GFRP. S0, G0 normal steel bar only used. G0 GFRP only used without cables. And this design calculation were conducted ignoring strength reduction factor specified in ACI. So the materials used, this slide shows the properties of steel concrete. As we can see, the yield strength is 511 with ultimate strength of 600, and compressive strength cubic of 40 megapascal. On the other side, the properties of Gfrp and Pt shown in this slide. As we can see, no yield in Gfrp with a tensile strength of 997. So as we noticed that no yield, which refers to it's a very brittle material and giving no warnings in the structures. That's why it's not preferable to use alone, as I mentioned before. For the cable, ultimate strength is 1860 with yield strength of 1670. The specimens were executed in a site and transported to a lab. These slides will show sequence of construction, reinforcement preparation, strain gauge installation, shuttering, casting, compaction, stressing, then finishing, and the lab. And the results. Before showing the main results, let's remember the stress strain curve, the famous one that all engineers know when we design any RC building. Normal steel pre-stressing cables, FRB, is mentioned, and noticing that almost FRB stress strain curve is linear. So the main result I want to discuss is a load strain, and G0 specimen, which is the GFRP only without any cable, shows this linear behavior, and the others TG1, TG2, and TG3, the specimens with GFRP and cables, show a curve almost similar to the normal as we know of mild steel or pre-stressing steel. So I want to spot the light on this curve. This curve is a preferable one to overcome the brittleness and change it to ductile. Okay. In the use codes, we can see a ratio of the experimental failure to code predictions for the tested beams with ACI, EC, Canadian, Egyptian codes. As we see, some codes show a high conservative ratio. Most are within the range. So as engineer, each country uses specific code. So just to know a quick comparison with codes and what's the best to design with, whether normal steel boards, beam, or GFRP, or mixed with cables. So it's up to you as engineer, the use codes and the country. So we can classify the conclusion into two categories. Number one, impact of using BT tendon with GFRP bars, and number two, impact of replacing steel with GFRP and BT beams, as this thesis was focused on a beam. So for number one, beam G0, which is pure GFRP, showed the lowest load with a high deflection at failure without showing any descending curve after reaching the peak load, which is common about GFRP. And compared to this beam G0, it can be concluded that using BT tendon, as mentioned, with GFRP enhances the behavior from brittle to ductile, and this is the point of overcoming the disadvantage of GFRP. The experimental results revealed that the beams with GFRP had smaller failure load and less cost compared to those with non-pre-stressing steel by up to 25 and 13% respectively. Knowing that this 25% can be reduced up to, let's say, 10%, as the used material was having a specific ultimate strength, can be improved if we used another one, but as mentioned, that was the available material in the Egyptian market in that time. As we can notice, the cost was less, and this is also of the advantage we want. On the other side, the weight of the used GFRP bars in each beam is lower than those of traditional steel bars by 72 to 89%, which is amazing percent. So we get what we want briefly from the thesis: lighter building less overall cost in the long term, almost same failure behavior load, and with the corrosion, magnetic field, sustainability, all other advantage we mentioned, with the super point of overcoming the brittleness which happened with the cables. That's why we get what we want. So the recommendation for future work to study long-term durability of BT with GFRP under various environmental conditions, including freeze-thaw cycles with dry cycles and exposure to more chemicals and fires. Implement a parametric study to assess the effect of changing wider range of parameters. Study the dynamic behavior on this combination, and why not carrying out flexural capacity prediction using AI or machine learning. That's the main point I want to discuss. Why we want to go through this combination, what we want to implement, and the future is taking us where exactly. I hope that more studies can be done to this topic, as it's very important. It needs more concern, and really it's a super combination. And finally, thank you. I hope that was an important discussion. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.